Today's episode is brought to you by Squarespace, because why not? They already sponsor half of the internet. How many subs do you have? 20? F it, here you go. Now, if in case some Google YouTube algorithm caught that last part, not the part, I can beep that out. But I'm not really sponsored by Squarespace. Please don't take away my little ad at the beginning or that little thing at the little yellow line. I need the nickel. I do use Squarespace for my website, but yeah, I don't have any codes. Here, these codes might work. I heard those recently. Give those a try. But anyway, today we're going to talk about net ionic equations. And we'll do 2 or 3 examples depending on how much time. Because again, I keep being told that if I can't do these in 10 minutes, the attention span of millennials is just, I don't know. So we'll try at least a couple. And these are from page 165 of my book. And it's not really self-promotion as much as it is me being a little lazy. But there you go. So let's look at this equation between sodium sulfide and hydrochloric acid to give you sodium chloride and hydrogen sulfide. So remember ionic compounds like sodium sulfide. Ionic compounds don't exist as individual molecules. You don't have sodium sulfide molecules floating around in your water. An aqueous ionic compound is actually dissociated. It's broken up into ions. So we can rewrite this equation a little bit where you actually show that. And we'll keep the phases if I can write them. Same thing with hydrochloric acid. Acids, they're an exception to how covalents behave in aqueous solution. I don't know why I couldn't get that out. But yeah, acids, they also dissociate. So those 2 hydrochloric acids, they will, generically speaking, break up into H plus and chloride ion. And I'll give myself some room down here. Now we're on the product side, getting the sodium chloride, again, it's aqueous, it's ionic. So it'll also dissociate. So let's rewrite that to show it as dissociated. And you'll notice I'm keeping the coefficients because that'll help in a lot of cases. But hydrogen sulfide, that's a gas. Gas. It's not dissociated. You either have actual hydrogen sulfide molecules floating around in the water, or what probably happened is when that hydrogen sulfide was produced, most of it all just bubbled out. So we're not going to break hydrogen sulfide up into ions because, again, it's not dissociated. It's a gaseous compound that's, again, either floating, or little of it's still floating around, most of it bubbled out when it was formed. So if you look at this equation when you write it this way, you'll see that sodium ion didn't really do anything. You have sodium ions in aqueous phase on the reactant side. On the product side, it's still an aqueous ion. So it didn't undergo any chemical change. It was an aqueous ion floating around in the water to begin with, and it's still floating around in the water. Same thing with chloride ion. All right, chloride, aqueous phase on the left, aqueous phase on the right. So these are what we call spectator ions. And spectator ions are just ions that don't do nothing during the reaction. They don't undergo any chemical change. Again, there were ions floating around to begin with. There's still ions floating around after the reaction's done. So if we remove the spectator ions from our equation, that's when we get what we call a net ionic equation. So a net ionic equation is just showing you the actual reaction that's occurring. And the actual reaction is sulfide ion and hydrogen ion reacting to give you hydrogen sulfide. And sometimes you'll use the entire equation. It's better to use the whole thing. Like with stoichiometry, that happens a lot, especially when you're dealing with masses, like gram to gram stoichiometry that you first do in the reactions chapter, probably the chapter before this one. A lot of times, the net ionic is actually more helpful. Like you're probably doing oxidation reduction reactions at this part. Probably right after you started talking about net ionics, you went into some redox stuff. For a lot of redox reactions, it's actually better. I can't talk today. To just get rid of the spectators and see what the actual reaction is. Let me drink something. So, essentially, a net ionic is just the reaction without the spectators, or the chemical equation without the spectators. So, look at another one. All right, this time we'll look at the reaction between zinc and hydrochloric acid to give you zinc chloride and a hydrogen gas. All right, so again, you start with zinc. It's in the solid phase. It's not dissolved. So a lot of times people will want to add a charge there and make that aqueous, or God forbid they just keep it a solid. Yeah, don't. If it's in the solid phase, you're not going to do anything. Again, don't add charges if they're not there already. All right. You just have a hunk of zinc metal that's in that solution, which if you're doing the lab component of a Gen 1 course, you might have done that reaction already, or one very similar to this. You might have taken a hunk of zinc or copper and thrown it in some solution. So yeah, if it's in the solid phase, similar to what we did before with hydrogen sulfide, you're going to leave it alone. Because it's not dissociated, it's just a hunk of metal in your water or aqueous solution. Hydrogen chloride, like before, aqueous phase, so we're going to show that as dissociated. And again, I like to keep the coefficients. So 2 HCl's give you 2 H's, 2 Cl's. But I can fit it all in one line. Zinc chloride, that's an ionic compound. It's aqueous. So we're going to split it up into ions. But hydrogen gas, again, it's not dissociated. It's like hydrogen sulfide before. Either gas, hydrogen molecules floating around in the water, or again, most of it probably bubbled out, fizzed out of the solution when it formed. So again, we're not going to do anything with H2. Like zinc, we're just going to rewrite it as is. Leave it alone. So now when you look at this reaction, to try to identify what the spectators are, zinc isn't a spectator. It was a solid to start with. Now it's an aqueous ion. So it's undergone some change. It's gone from a metal to a dissolved ion. Hydrogen, sort of, kind of, but flipped. It started off as a dissolved ion, sort of, kind of. We talk about hydronium later, or I will. Your teacher may have already talked about it. But for now, H plus to start with, but as a product, it formed a diatomic gas. So that's different. But chloride, it looks exactly the same in the end as how it started. Chloride ions to start with, chloride ions to end. So yeah, in this case, chloride is our spectator. So you remove the spectator, you get our net ionic equation, which is zinc and hydrogen ion reacting to give you zinc ion and hydrogen gas. So at this point you can see that the only thing that we're breaking up into ions are aqueous compounds, which isn't entirely true. Like if you're already talking about strong or weak acids, there's a little exception there. But me, I save that stuff until General 2. For the most part, if it's an aqueous compound, you break it up into ions. If it's a solid, gas, or liquid, you'll leave those alone. So you only break up aqueous phase compounds, which again are ionic compounds or acids. Solid, liquid, or gas, leave it alone. Just rewrite it exactly the way you see it in the original equation. So one more to bring up one more point. Let's look at this reaction, which you might do in a lab, especially if you're one of my students. You do. But unless you're taking the online lab, then yeah, we don't do that one. I don't let you work with concentrated nitric acid at home. Sorry. But if you want to figure out the net ionic, back to the point, Mark. Again, just starting with copper, it's in the solid phase. Leave it alone. Leave copper alone. Aqueous, forgot to turn my phone off. Is again nitric acid. It's aqueous, so we break it up into H plus and nitrate. That's our reactants. On the product side, we have copper 2 nitrate. So again, if it's aqueous, break it up. Phase. NO2 is a gas. Gases, leave alone. Water is in liquid phase. Leave it alone. So again, aqueous break up, everybody else leave alone. So there you can spot the spectator. Which spectators, they just haven't changed. So copper is a solid on the reactant side. On the product side, it's an aqueous ion. That's not a spectator. H plus, aqueous on the left. Now it's part of water on the right. That's not a spectator. It's undergone a change. Nitrate. In nitrate's case, yeah, I forgot to put the aqueous there. Yeah, it's aqueous ion on the left. On the right, some of it's still aqueous ion, but some of it was converted to NO2. So, yeah, we'll go ahead and circle it. But this happens every now and then, where the spectators, only some of the ions are spectators and others actually react. Before, you'll notice we had the same number on both sides, like 2 chlorides on each side in our previous example. But yeah, sometimes you can have a different number, and that just means that only 2 of the nitrates are spectators and the other 2 are reacted. So those we'll take out. So you lose both of them on the right, but there's still 2 that remain on the left. So again, you rewrite everything without the spectators. We got copper and 4 hydrogen ions plus 2 of our original 4 nitrates. Give you copper ion. Nitrate, none on the left, it all dropped out. But NO2 is still there, and so is water. So that's our net ionic equation for this reaction. And you can kind of see, especially in this last example, basically what we're doing with net ionics is we're doing some algebra stuff with a chemical equation. Because you'll see this as we start to go deeper into chemistry. A lot of the things you can do with algebraic math equations, you can do those same little tricks with chemical equations. So instead of x's and y's, you're using elements. Like in this case, once you show all the dissociated ions as dissociated, you're basically simplifying the equation. But again, instead of having 4 x's on the left and 2 x's on the right, you got 4 of a polyatomic ion. And you could go even deeper with the algebra analogy, but I won't do that. But yeah, it's nothing entirely new. It's getting some algebra stuff that you're kind of applying to chemical equations. But the important thing to remember, especially this early on in what is, I'm assuming, Gen Chem, is that for the majority of you guys, it's just, if it's aqueous, break it up. If it's any other phase, leave it alone. Again, that's not entirely true. For some folks, you might have already learned about weak or strong acids. There's some stuff in there that makes things a little bit more complicated. Only a little, though. But again, I don't deal with that until General 2. A lot of teachers don't deal with that into General 2. So for the most part, again, aqueous, break it up. Everybody else, leave it alone. Don't do anything to it, just rewrite it. And from there, you can see what the spectators are. You know, it looks exactly the same on both sides. You remove those, that'll give you a net ionic equation. All right? All right, so that'll be it for this time. I will see you next time. Anyway, bye. Today's episode is brought to you by Squarespace, because why not? They already... Try it again.